it's important to well characterize the instrument. One parameter of the long list of parameters is to characterize the surface analyzed, and this in the different modes who exist in your instrument. One way to work in terms of spectroscopy independently of the instrument kind is to move the sample to have a sharp edge through the beam, and this will be allowed to characterize the surface analyzed. Here you can see a file, then you have in column for one kinetic energy, the intensity at different position, and so if you take a row, you have on one position the different kinetic energy, and we're measuring first in each position the different kinetic energy, and this will create the whole data. So first thing that we have to do is edge times, and we have, but that is sample position, and we can add the facts and the measurement when done in millimeters. The first step that we have to do is to measure or to quantify the intensity. For this we will use a zero background. We want to see the intensity above the zero line. Of course, when your sample is not inside the beam, you have no intensity, and we have to do it column by column by the fact that the kinetic energy is different for each column. You can't use propagation. Now, one advantage, you can use a way to propagate all the backgrounds that you have done for the first row to each column with respecting each column. So now it's done. Have you seen it? Now you can see that for each measurement the background is done. The fact that we have a blue background on the left window indicates that the background is done. Now we will create the profile of intensity, and that is an easy job. And if you look on the second row, you can see that all the intensity, and you can see some very nice step function. And if you use double normalization, you can immediately see that all the full width is about the same, and all position of the center is about the same, meaning independent of the kinetic energy. This has to be tested. You cannot make the assumptions and your instrument is perfect. You have to verify, and in function of the modes, and you will be necessary one. If you're looking for, you will be find some trouble. Sometimes they are small, sometimes not so. One way that you can proceed is to make a fit, and you can use a step up, and you can fit the edge by this way, when by clicking on the region box, and now you can see the full width as the XPS company defined. But you can also use the copy data that we have done, and you can make differentiation to have a better viewing of your resolution, because now you can see your resolution as a peak, and you will be able to characterize the peak. As the measurement is done, the second row corresponds to the integrated spatial resolution, and the third row corresponds to your resolution. First we have to make the background, and this time we want also to make it each background individually, because we want to keep the information of the kinetic energy in the name of the region. And as you can see, we have the ability to change of spectrum without changing the size of the display. So we will use a part of the x-axis to make the background, but we can propagate in this manually way the regions that we want to have as a background. The facts and the data are integrated and smooth by the fact that we make a derivation. We have to use the RMS, and you can see that if you use the RMS, the standard deviation is very low. It's just meaning by the facts and our data do not respect the low portion. So now we can make a fit, and what we is our data as very close to a Gaussian, so it's meaning that our beam shape is very close to a Gaussian shape with an information that you can't see directly when you fit the step function. Again, we do it manually to keep the information of the kinetic energy in the name of the fit. So now we will be able, using annotation, to see the parameters of our fit. You can see that the position is very stable, and if we add the full width, you can see also the full width is very stable, and this time the full width is defined as a normal way, and we use the 1684% corresponding of the Gaussian. So that is really. Now we can also play a little bit, change the title to preparing to make a view graph in PowerPoint. So it's easy to do it, but you have to do it in the right way. In this case, we can precise the percentages that we use and the modes that we characterize. One easy way we can directly copy the data, and we make a copy like we see it on a display. In this case, it's a little bit too big, so we can change in Casa the size of the windows, make a copy again using size title display, and we can go back to the presentation and put back with the right size our results.